Good morning, good afternoon, good evening, depending on where you are. Welcome to this webinar. My name is Simon Ritter. I'm the Deputy CTO at Azul. As you can see from the title, what we're going to be talking about is the new features that are included in JDK25. And I think it's quite an interesting sort of alignment of things because we've got version 25 of Java in the year 2025. And we're not going to change the numbering scheme so that we start numbering it based on year and month. We're definitely not doing that. And we're also the 30th anniversary of Java, which is kind of interesting. So lots of history has gone on, and now we're still seeing new features being added to the language. Just a little bit of housekeeping before we get into the main part of the presentation. We will be recording this session and we will send you a link to it afterwards so that if you want to share it with your colleagues, with your friends, with your family even, then please feel free to do so. If you do have questions as we go through the presentation, I won't be taking them as we go through, but if you can type them into the chat box, then I will handle those at the end of the session and address anything that people want to know more about. So without further ado, let's get into JDK25. First thing is let's look at the sort of statistics, if you like, of what JDK25 includes. Now, the way that Java is being developed now is more through the Open JDK. It used to be that we had the Java SE specification, and the development work of that really went on through the Java community process and the individual JSRs. But that's shifted now, and because JDK consists of more than just the Java SE specification, we have these things called JDK Enhancement Proposals, or JEPS. And the idea of those is to provide a formal specification for a smallish piece of work. So it's not a huge project, but it's also not like an individual sort of few line change. It's a sort of reasonable chunk of work, but not huge. What we then have as well within the Open JDK are bigger projects that consist of a number of JEPs. So that's the sort of like next level up, if you like. And we'll talk about some of the projects that are involved in the features that are being added to JDK 25 and other things as we go through. Looking at the numbers for JDK 25, we have 18 JEPs included in that. It's a little bit more than the average. I worked out the average is 13 JEPs per update. So JDK 24 had 24 JEPs in it, so that was a bit higher, but 18 is a good number. The way we're seeing development of Java at the moment with the 6-month release cycle, obviously some have more, some have less, depending on which features are ready to be included. Now, what we've got here are a number of features which have previously been preview features or experimental features, and they've now been made final. So I'm not going to spend a lot of time talking about those specifically because in the case of those, I've probably talked about them in previous webinars, and the changes to these are fairly minor. So essentially, we've got 7 of those JEPs which relate to things which are now final. So I'll just briefly talk through those. Scoped values is sort of part of Project Loom. It's the idea of how you can replace thread local variables and have a better way of dealing with variables that you want to share between multiple threads in concurrent programming. So it's an API that makes life easier for that, especially when you link it together with the idea of virtual threads. And we'll talk more about that when we come back to some of the other things which are going on in that space as well. Key derivation API, it's an API that allows you to create cryptographic keys. Again, sort of providing more facilities from a security perspective, different ways of generating those keys and so on. Module import declarations is a fairly small change. What it does is allows you to simplify the way that you can include all the elements of a number of packages, rather than having to go through and deal with all of the individual packages in a module and do an import of those packages, even using the wildcard start operator. Now you can simply say import everything from this particular module. It just makes life a little bit easier for developers in terms of what they're using. Compact source files and instance main methods. This is related to the idea of trying to make Java easier when you start programming. When you write your very first Java program, it's typically going to be something along the lines of hello world. And the kind of criticism of Java is that there's a lot of ceremony involved in writing that very first program. And by ceremony, they mean lots of boilerplate code. You have to create a class, you have to then have your public static void main method, you have to have string array args that you pass into that, none of which you really need if all you're going to do is print out a message which is hello world. You still need system.out.println for that particular message. What they've done here is to try and reduce that, so now you don't have to specify all of the details of that, and you can strip that down to a fewer lines of code. My personal feeling on this is that it's a nice idea, but it doesn't really move the needle much in terms of Java. Once you go beyond hello world, you still need to understand all of that ceremony. You need to understand the whole process of creating classes. You need to understand how the main entry point works and all that good stuff. So yes, it's a nice idea. I'm glad it's in Java now, but I'm very happy that we don't have to talk about it anymore. Flexible constructor bodies. This is very useful because if you look at the way that Java has been defined, if you're creating a constructor and you want to call the constructor of the superclass using the super method, then that has to be the very first line in the constructor. And that sometimes is a little restrictive because if you're looking at parameters that are being passed to the constructor, you may want to do some tests on that to see whether they actually comply with what you want to do in the constructor. If they don't, you could throw an exception. But in this case, you can't do that until after you've called the superclass constructor. So now with flexible constructor bodies, there are certain things, not everything, there are certain things that you can do before you call the superclass constructor. So that kind of thing, very useful in terms of just making Java a little bit more flexible in terms of allowing you to do things like that. Compact object headers, this is related to the way that the JVM works. In the JVM, clearly we have objects that are represented in the heap, and we need a pointer into the heap to know where that object actually resides. The header is 128 bits in the past, and now we're compressing it down, if you like, or reducing it down to 64 bits. This might seem like a small change. Well, it is, because it's 64 bits of change, but that actually can have quite a significant impact. And if you read the JEP on this, you'll find that there are a number of situations that they've tested this with, and it's resulted in quite a significant saving in terms of the amount of space and memory that's required to handle all of the objects in benchmarks and so on. So this is a very useful kind of thing to include, again, to improve performance, especially if you're doing things like microservices and trying to get the smallest possible footprint for your applications. Last thing there is generational Shenandoah. Shenandoah is a garbage collection algorithm that initially started by Red Hat, contributed to the OpenJDK. When they started that project, quite a long time ago now, actually, they decided that they wouldn't use a heap that was divided into generations, the young generation, the old generation. They went with a single heap space, and they discovered that the performance of Shenandoah wasn't as ideal as they wanted to. So they went back and understanding the idea of the weak generational hypothesis, which says that most objects that we create are only used for a very, very short space of time. Then they decided to rewrite part of the garbage collector so it would use a generational heap space. You could still use it without the generational heap space, but now you can also have it with young and old generations. So we have 4 preview features, which I'm going to talk through, 1 experimental feature, which I'm also going to talk through, and then 1 incubator module. Incubator module kind of related to preview features, but in this case, it's related specifically to APIs. The Vector API holds the record now for the longest incubating API, 10 iterations. Why are we still iterating it after 10 different versions of Java? The reason for that is that there isn't really much changing. If you look at the JEPS recently, nothing major has been changed, although I think in this, in JDK25, we did actually change a few things. But specifically, the reason that it's still an incubator and will continue to be an incubator for the foreseeable future is because it's related to another one of these larger projects, which is called Valhalla. Valhalla is about adding value types to Java, and the decision has been made that until other parts of Valhalla are delivered into the JDK, they don't want to finalize the Vector API in case some of those things that they deliver actually result in changes to the Vector API. So let's keep it as an incubator. Once all the changes have been made for Valhalla, then they can say, right, finalize it, and off you go. It can still be used quite happily outside of Valhalla, has a lot of benefit in terms of where code is not auto-vectorized by the compiler, and you can explicitly state how you want your arrays of data to be processed in terms of populating your very wide registers and doing your single instruction multiple data operations on those. Right, let's move on. Now, I have divided this into language features, API features, and then JVM and other things related to the JDK. So 3 different sections. Starting with the language features, not really a lot. There's only one particular thing which relates to language syntax specifically, and that's the idea of using primitive types in patterns for instance of and switch. What we're doing here is allowing Java to be more flexible in terms of the types that you can use these pattern matching with. If you look at Java, Java is an object-oriented programming language, but it's not a pure object-oriented language. We still have primitive representations, int, float, and so on. And the reason behind that was when Java was first created 30 years ago, the designers said that in terms of performance, if they treated everything as an object, they weren't going to be able to get the performance they needed to run applications the way they wanted to. So they said, we'll allow primitive types because they're easier to handle. You don't have that object reference. You don't have to necessarily go through the heap and so on. And it just makes life easier. The limitation of that is that you can't treat a primitive as an object reference. So it doesn't have a type in the true sense within Java. That's why we have the wrapper classes. So int has an integer class, float has a float class, and so on. Now, what they've done here, they've said that with the introduction of pattern matching in instance of and switch, where now we can actually test for a type as well as a value, we can also include the ability to do that on primitives as well as the object representation of those primitives. Again, this is part of the larger project, Project Amber. Amber is all about looking at how to improve the language, taking some of the rough edges off where things are less than ideal, limiting or reducing the amount of boilerplate code in certain situations, and so on. Since the preview, nothing really major has changed. Just to give you some examples of how you can use this, very simple. Here I've got an int I, which I've assigned a value of 42 to, and then I can do a test on that. I can say if I instance of int, and the compiler will allow me to do that, and it will say, is that an int? Yes, it is. So it will then do whatever the true branch of that if statement is. We can use it with a switch as well. So now we can say switch on I, and then we can have case byte B, print out byte, case int I, print out int. Now, the interesting thing about this is that in this particular situation, what's going to happen is that it won't be a compile time check. It'll have a runtime check as well. The reason for that is that what the compiler and the JVM needs to do is to evaluate whether the value of I will fit into a smaller representation. And what I mean by that is that in the case of 42, that will fit into a byte. Byte is 8 bits, so we can represent 42 in 8 bits, no problem. So in that case, when we run this and we do switch on I, we will actually get a byte, even though we've declared it as an int. We'll get a byte because it will fit in a byte, and so the result will print out byte. That's all good. What's a little bit more interesting is that we also have a situation like this. In that previous example, if we reverse those two lines, so we have int first and then byte afterwards, that code won't compile. The reason it won't compile is because you've got pattern dominance. Everything that will fit into an int, everything that will fit into a byte will also fit into an int, which means that if you pass in 42, for example, which would fit into a byte, it will always match against the int if it's first. And that means you'll never get to the byte. So the byte is effectively unreachable. That's pattern dominance, so the compiler will reject it. Okay, fine, I get that. I understand that. That all makes perfect sense. What I don't understand is why this code compiles. So if we change the int to an integer as the wrapper class, even though we still keep our I as an int, that will auto box and we will get int printed out. So the compiler is actually saying, yep, I'm quite happy with that. And it's ignoring the fact that the integer class will still dominate the byte primitive. I've asked a question on Stack Overflow, or I've asked this question to the Amber expert group, and I still don't understand why that does work. At some point, somebody's going to explain it to me. Next, libraries. What do we have in terms of those? First of those is stable values. And this is quite an interesting sort of thing, because if you look at Java, Java is, again, object-oriented, so we store things in objects, we have state associated with those. But often what people want to be able to do is to create objects which have immutable values inside them. Immutable meaning you can't change them. And the only way that we can do that within Java is to mark variables that we want to be immutable as final. So, okay, great. So you mark something as final, and the idea is that its value is set once and it can't be changed. But the problem with using final is that it has a number of sort of drawbacks to it. The first is that you have to make an assignment, or you have to initialize the value of that either statically or during the object creation. And that means that you're restricted in where you can actually make the assignment to that variable. It has to be either an object creation or statically done. You can't wait until later on when you've calculated something or decided what you want to put in there. The other thing about final is it's not truly final. If you look at the way final works, yes, you can set something to be final, and you can say final int I equals 42. If you then try and change that by saying I equals 52, the compiler will say, no, you can't do that because it's a final variable. You can't assign a value to it. Great. But if you use a reflection, deep reflection specifically, you can make that variable changeable and you can change it through reflection. So you can set it to 52 if you really want to. So it sort of limits the scope of what we can do with immutability in Java. What they're doing with stable values is to introduce an API, so not part of the language specifically. This is an API that's doing this, and say, okay, let's change the way that immutability works from this perspective, meaning that we can have something which is defined as being a value which is only a variable that's only going to have one value, and that value, once it's set, cannot be changed. So same idea, but in this case, what we're doing is we're separating out where you define that variable and where you initialize it. As long as it's initialized once and only once, then that's fine. But you can do that anywhere that makes sense for your application. Also, like I said, decouples the creation of the stable values from the initialization. Also guarantees that stable values are initialized only once, even in multi-threaded code. So all of that is taken care of for you. And this will actually allow us to improve performance through what's called constant folding. Now, constant folding is essentially where you say, if I've got something which is storing 3, and I know it's immutable, and I've got several other variables that also store 3, rather than having to have multiple copies of 3 or a string or whatever, then I only need to have one copy because I can share that and I know it's not going to change. Structured concurrency is the next one we need to look at. This is, again, preview feature, now in its 5th iteration of preview. Also linked to Project Loom, linked to the idea of virtual threads so that we can have better scalability for applications that use large numbers of threads, specifically in situations where you're using something like a web server and you have a thread per request model. And those threads that are handling one thread per request are also doing a lot of blocking. So they're going off to a database, they're going off to a file or a network connection and spending a lot of time blocking. What we can now do is we can say, right, let's have a virtual thread where rather than each Java thread mapping to an underlying operating system thread one-to-one, we're going to have multiple Java threads mapping to a single underlying operating system thread. And it's the JVM that handles the scheduling of those Java threads to that underlying operating system thread. It does that by waiting for a thread to block, and when that thread blocks, it will say, okay, I can remove that one from the what's called the carrier thread, and then I can take one of the other ones that's assigned to that and then put it on there, allow it to do some work until it blocks, and then switch between that. One thing that you need to understand with virtual threads is there's no preemption. So you have to basically give up the thread in order for it to switch to another Java thread. Related to that is this idea of structured concurrency. And this is a really nice idea, I think, because it allows you to simplify the way that you have various tasks which are linked together in a concurrent situation. The example here, so we've got something which is handling a request, and what we can do is we can define a structured task scope. So we're going to have a number of tasks within this particular scope. And this is similar in many ways to if you look at the way that try with resources works. That was a great inclusion because try with resources says, okay, so you've got a try block and you create a number of references to things that implement the closable interface. When you exit that block, you're guaranteed that all of the closed methods on those objects will be called and everything gets tidied up for you. So when you exit, everything's nice and easy. You don't have to put that, try catch finally block in there to make sure everything works. All gets done for you. It's the same idea here. So we're taking a section of code using the try block and saying, okay, the scope that we're going to use for this is a structured task scope. And then we're going to create two subtasks in this particular situation where one is going to fork off a separate thread and say, call the find user method to return a string. And then we'll fork off another thread, which will go off and do the fetch order, return an integer. So we've got two separate tasks happening concurrently. And then obviously we want to bring those results back together when they're both ready. That works really nicely because you do scope.join, and the scope.join will block until both of those things return. Now, if something happens abnormally, one of those threads decides that it can't call the find user, for example, the exception gets thrown. What will then happen is that will also get caught very nicely and handled within the structured task scope. So you either get full completion, or if an exception gets thrown, then it will also kill other threads which are working so that you don't waste time waiting for a result from fetch order when you know that you're never going to get something from find user. So it's a nice way of tidying everything up and making it all very easy from a coding point of view. I really like this particular feature. The third thing that we've got in terms of APIs is what's called PIM encoding of cryptographic objects. And this is about encoding cryptographic things, specifically like keys and certificates that we need to move around in order to have communication which is encrypted and both ends of the connection can share details and then do whatever needs to be done. The way this works is essentially like doing a UU encode. So it's taking binary data and translating it into data which is text in effect, which can be sent through email. Rather than just using UU encode, this is a more sort of higher level, more complex format for the data, and it uses what's called privacy enhanced mail. So there's a well-known format for sending binary data through that, and in terms of cryptographic details. So what we've now got within Java is an API to do that. What you'll find is that there are quite a few classes around the cryptographic side of things which implement this interface called DER encodable, which says that they are encodable in this format. That way you can do that directly. So you just call a method on the object you've got, and that will return the encoded data for you. If the object that you're working with doesn't implement the DER encodable interface, then you can use the PEM record class, and you can essentially do that yourself. So it's a kind of more manual labor kind of thing to get the same result. Okay, JVM and other changes. There's a couple of sort of sections here. So the first of these is related to yet another one of these projects that we have in OpenJDK, which is Project Leiden. Project Leiden is looking at how to improve the startup and warm-up time associated with Java applications. If you think about the way Java works, we compile our Java code into bytecodes. Bytecodes are instructions for a virtual machine, hence the Java virtual machine, rather than the physical machine that we're going to run our application on. This is, has been right from the very beginning. This is the way that Java works. It's what gives us the ability to have write once, run anywhere, compile into one class file, one jar file, and you can run that whether it's on Windows, on Intel, Linux, on ARM, doesn't matter, because it's the virtual machine that does the translation. Now that's all very good, but the problem we see is that when the application starts up, because the JVM starts up in interpreted mode, converting each bytecode as it finds it into the necessary instructions, the program runs very slowly. As we run the application, the JVM will profile methods to see how many times a method is called. When a method reaches a certain threshold, it will get JIT compiled, just in time compiled. So the method gets passed to the C1 JIT compiler, compiles it into native code. We run that, so it improves the performance because now we've got a set of native instructions to run, but we also profile it to understand how that method is being used as the application actually runs. When we get to another threshold for that particular method, we'll then recompile it with the C2 JIT compiler, and that will take the profiling information, optimize much more heavily based on the understanding of what the code is doing, and then generate the optimized code so that we can then run that even faster. More methods as we run the application will get compiled, C1, C2, profiled, and so on, until we get to a point where all the frequently used methods have been compiled. That's our warmed up state. Problem is that when we run the application again, we have no memory, so we just go back to the beginning and we have to identify the methods, we have to profile them, compile them, and so on. Project Lightning is all about trying to improve that. And they've done this with a set of what they describe as ahead of time components. Now, this is not like ahead of time compilation. So if you look at things like GRAL native image, that's ahead of time compilation. What you're doing is taking your Java code and compiling it directly into Windows and Intel instructions or Linux and ARM instructions. So you have a targeted application. In this case, we're still doing bytecodes, but we're using information that we can record from a run of the application, feed that back into the application when you start it again, so you have ahead of time information. First of the JEPS that we've got here is ahead of time command line ergonomics. Now, the way that this worked when it was first introduced was to say, okay, run your application, let it warm up so you get to your steady state maximum level of performance, and then you take effectively a profile of information about what has been done using the JIT compiler and so on. Now, the drawback with the way this worked was that you could take that profile, but you couldn't directly feed that profile back into the JVM when you started up the application again. There was another step involved, which was where you had to generate the representation that would be understood by the JVM. Now, that didn't really make a lot of sense because, of course, you're taking the profile, generating some data, then you have to convert that data before you feed it back into the JVM. Why not just do it all in one go? Because if you're generating data, generate it in the right format for the JVM. That's what they now do. So improved command line ergonomics reduces that from 2 steps to 1 step. So you now collect a profile and you can just feed that directly into your JVM when you restart it. So yes, that's all good stuff. Streamlines how you record and create your models for the into a single run. So that's all good. Now, Azul has technology which is very similar to this. It's called Ready Now, been around for a long time. We had it in our platform Prime. Does all of this plus a lot more in terms of the JIT compilation and stuff like that. So if you're interested in that, have a look at what we're doing with platform Prime. The second thing which has been included, again, related to this Project Leiden, improving the performance of warm-up and startup, is around method profiling. And as I said, when you start up your application, JVM will count how many times methods are called, and then when it's compiled with C1 code, it will then profile that method to record information about how the method is being used, and that will be fed into C2. What we're doing now with Project Leiden and ahead of time is the profile that we generate, the cache of information, is now going to include more information about method profiling. So this will allow the JIT compiler to do more work as it starts up and do more work ahead of time before you get to your main entry point and actually do the work of the application. So still identifying hot methods, still collecting profiling data, but now what you've got to remember is, yeah, things will kick off quicker. The second sort of big section of things that we've got in terms of the JVM and JEPS is around Flight Recorder. So you've got Java Flight Recorder. Now, Flight Recorder is a really good tool. What it does, it allows you to collect information about what is happening as your application is running. And you can do that in a couple of different ways. So you can monitor a live application. You can use Flight Recorder as a way of interacting. You can use a tool like Mission Control. Mission Control will interact with the flight recorder data so that you can see what's actually happening in a running application. But there's a second way of doing it, which is to say, okay, if your application stops abruptly, has an error, whatever, and you don't quite understand why it stopped abruptly, Flight Recorder will produce a post-mortem set of data. So it will record everything that was happening when that application stopped. And you can do a post-mortem analysis of that to say, oh, okay, what was going on? What were these values? What was happening? And then you can decide, oh, okay, now I understand why my application stopped the way it did. Now, this is all very good. And one of the nice things about Flight Recorder is because it's baked into the JVM, it takes advantage of a lot of the data which the JVM collects in order to do its work. So this method profiling that we talked about for AOT, that's one of the things that we can take advantage of, because we can see how many times methods are called, because the JVM will record that as part of its JIT compilation. Lots of other data that we can get at because it's recorded by the JVM. So now what they're doing is trying to sort of take that further to give us even more information and give us better ways of collecting data about the way your application is running. Because one of the sort of struggles that we have when we're doing profiling and performance data analysis is that you don't want to bump into the problem of Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is actually to do with quantum mechanics. What it says is the act of observing something changes what you're observing. Now, that's great in terms of quantum mechanics, but it also applies in terms of computing. Because if you start putting lots of profiling measurement points into your code or into your JVM, the fact that you're collecting all this data and having to write it out somewhere or record it somewhere actually distorts how your application runs, because it'll slow it down. So you're seeing your application performance degrade just because you're collecting profiling information. So what we want to do is minimize as much as possible the impact of collecting the information on the performance of your application. So one of the things that they're doing here is adding CPU time profiling so that they can do this on Linux and get more information about how much CPU time is being used by the application. And it's doing it through sort of digging deeper into the operating system to collect data that the operating system is recording about how an application works. So we can take advantage of the JVM information. Now we're taking advantage of more information that's coming from within the operating system itself. Experimental feature, only on Linux. Second thing is, again, Flight Recorder, but this time we're talking about cooperative sampling. And this is where we really do see the problem of Heisenberg's uncertainty principle, because what happens here is that we're trying to analyze what's happening in terms of the performance and looking at how much time is used by different things. And the way that this works is that in order to collect reliable information, the threads have to reach what's called a safe point. So a safe point is a known state where nothing is essentially happening. And you can say, right, collect my data at this particular point, and I know that I've got the right data for what my application is doing. Problem with that is that this leads to what's called safe point bias, or the safe point bias problem. And it's essentially saying, well, okay, well, if you have to reach that safe point and you're only collecting that information there, then you're not really seeing a true representation of what's actually happening. So now you've got a new way of collecting sampling data for timings, when you need to do that within the Flight Recorder, it will register a sample request for a particular thread. And then when that thread reaches the safe point, if there's a sample request exists, it will collect the necessary data. If not, it won't. So again, what this is doing is making the Flight Recorder data more accurate. So you get a better picture of what's happening in your application performance. And then the last thing is the idea of method timing and tracing. And this is the one where we really do see the impact of adding profiling information to an application can really degrade performance. If you start tracing every method that you're calling, and when you enter a method, you need to record, let's say, the time, you need to record what the parameters were that passed that method. And then when you exit the method, you also need to record the time so you can see how long you spent in that method and maybe the return value. That places an enormous overhead, because you wouldn't believe how many method calls you do. It really is quite stunning when you dig down into the data and you realize that you call a method in a library, and the number of method calls that results in terms of underneath that, they can be literally one method call can result in millions of method calls. I've actually done some work on this myself and seen that. But anyway, what we want to be able to do is to focus our attention on specific methods rather than every method. And that's what this method timing and tracing JEP allows us to do. What we're now going to do is have bytecode instrumentation, which we can inject into the running JVM, into the class file, which says, okay, well, this is the method I'm actually interested in. Let's put some extra bytecodes in where we enter that method so we can collect the timestamp where we entered, we collect information about the parameters, and then we'll add some bytecode at the end when we exit so that we can collect the time and, if necessary, collect details about the return value, but only for that particular method. So if all the other methods don't do that, we're only focusing on one, the distortion in terms of performance is going to be significantly less. Obviously, the more methods you start profiling at the same time, the more impact it's going to have. But if you're trying to target specific methods and you really need to know the details of those, then this is going to really be helpful to you. Different ways of invoking this, you can do it through command line arguments, so you can start it up when you start your application. You can do it through configuration files, so that you don't have to put command line arguments there. You can use the JCommand tool on a running application, and you can even do it across a network if you want to via the JMX interface, the Java management extensions, and you can tap into a running JVM as long as you have the right permissions, and you can enable various things through that. Last thing to talk about from the JVM and JDK perspective is the removal of the 32-bit x86 port. This is something that they've been working on for a little while now. These ports have been scheduled for removal for a couple of releases. And in fact, if you look at JDK24, the Windows 32-bit port was removed. And now what we're doing is removing the Linux 32-bit port. So there is no longer going to be any 32-bit ports in JDK25 onwards. Kind of makes sense because there aren't that many people out there using 32-bit operating systems unless you're in the embedded space. I know there's plenty in the embedded space, but if you're using desktops and servers, anybody using a 32-bit server anymore? So you could have potentially Windows XP, I guess, on a desktop. But if you were going to try and move your application to using JDK 23 or 24 or 25, then most likely, if you're going to make that kind of level of upgrade, you're also going to upgrade your operating system at the same time. So this makes a lot of sense to reduce the amount of work that's involved in maintaining a port which very, very few people are going to use. So that's why we've done that. Last thing to talk about is what I call the Oracle JDK21 time bomb. What do I mean by this? Well, if you look at the licensing that Oracle use for their JDK, right now, when you have a new long-term support release, and JDK25 is a long-term support release, what the license or the license that is used by Oracle for their JDK is what they call the no-fee terms and conditions license. And that has a clause in it which says you can use it without a Java SE subscription, so that means for free, for internal business applications. That's different to other licenses where you're only allowed to use it for development, testing, prototyping, that kind of thing, or personal use. So if you're using the NFTC license, internal business applications, you can use the Oracle JDK without buying a subscription. Great. But the NFTC does not apply in perpetuity. It only applies until 1 year after the release of the next long-term support version of Java. At that point, all subsequent updates to the Oracle JDK will revert back to the other license, or one of the other licenses, which is the Oracle Technology Network License Agreement. And that's the one where if you want to use it for pretty much any business application, you will need a Java SE subscription. And the price of that Java SE subscription will be based on how many people you employ, not how many Java instances you use. So what I've tried to do here is to represent graphically the impact of that. So what you will have found is that JDK21 will have been under the no-fee terms and conditions license, and that will now revert to the OTNLA license 1 year after JDK25's launch, which is this week. So that's 1 year from now, September 2026, which means that the October 2026 update will revert back to the Oracle Technology Network License Agreement. We've already seen this with JDK 17. So JDK 17 has reverted back. So any updates that you're using now will be under that license, meaning you need a Java SE subscription. This means that you do have sort of choices about what you can do. You can say, okay, in 2 years' time, or 1 year's time, I'm going to move to JDK25. And then 2 years after that, I'm going to move to JDK29, which will be the next long-term support release, and so on. And you can continue to use that free license. Otherwise, you need to pay for a license from from Oracle, or you can switch to a different OpenJDK distribution, such as a Platform Core from Azul. If you're thinking about moving from the current long-term support release to this new one, JDK25, then there's a few things to think about. First of all is stability. Do you think that with JDK25 being released this week, is that something you want to deploy straight into production, or do you want to give it a little bit of time to allow people to do various testing on it, make sure there's no things that we're going to catch you out for your applications? I would expect most people will wait at least 2 updates, probably even longer than that. They may even wait up to a year for stability to make sure there's nothing that's changed which will cause any problems for applications. Very, very important, though, is to test your applications with JDK25 if you're planning on migrating to that, so that you know of anything that will potentially affect your applications. Incompatibilities. Java has been very good over the years about maintaining backwards compatibility. You can literally take code that was compiled with JDK 1.2 and run it on JDK 25. That will work. Not every piece of code will do so, but most will. And one of the things that did change with JDK 9 was we started removing things like the 32-bit port, as well as adding things. And that has potentially some impact if you've used any of these things that get removed. Typically, the stuff that gets removed from JDK is quite esoteric. So few situations where you're going to bump into this, but occasionally you do. Good example here, the security manager is now permanently disabled in JDK 25. As opposed to JDK 21. Don't worry about that. When we talk about the security manager, we're not talking about reducing the security of Java. What we're talking about is the security manager that was really used for applets. So if you're not using applets and you're not moving to JDK 25, then nobody would be moving to JDK 25 if they're using applets. But I have seen customers who have taken advantage of the security manager outside of applets because it had the right functionality for what they were doing, and they are now a bit stuck in terms of moving to JDK 25 because there is no alternative to that. There is no different way of doing the same thing, so they're looking at having to rewrite part of their application to do that in a different way that does still work. A couple of other things that have been removed. Perf data sampling has been removed. If you're relying on that for whatever reason, then you need to take account of that. Again, very esoteric. The Sun PKCS 11 BPE secret key factory implementation has been removed. I'd be very surprised if anybody's actually using that, but I'm sure somebody will prove me wrong on that. And then finally, the java.net socket has got some deprecated constructors, which means that you can't create a datagram socket from socket directly anymore. So if you use that in your code, that might be something that catches you out, then you need to be aware of that. Similarly, with libraries, if you're using libraries, which most people do, then are your libraries ready to work with JDK 25? Have they been tested? Have people make sure that none of these things will catch them out? This is also a good opportunity to look at dead code elimination. If you've got a long running application, one that you've been developing over many years, there might be application code which is no longer used. So it would be an opportunity to remove that. Azul's Code Inventory can help you with that. If you're interested in that, have a look at our website. To conclude then, JDK 25 is very logically, the next version of Java. It is 6 months worth of development, and it includes a number of interesting features as we've gone through. I think Java Flight Recorder is probably the highlights there. Some of the Leiden stuff as well is interesting. It is a long-term support release, so that means that OpenJDK distributions will be providing extended maintenance and support for it. That makes it more appealing for deployment for production. Which distribution you decide on will decide how long you get extended maintenance and support for. So think about that when you're looking at which distribution to use. We can provide you with extended maintenance and support for JDK25, but also for JDK21. So if you want to continue running JDK21 in production, also if you want to continue using JDK17 or 11 or 8 or 7 or even 6, then you can, because we still provide updates and support for those versions. So with that, I am going to end the presentation part of the webinar, and then what we'll do is, like I said, if you do have any questions, then please feel free to type them into the chat box. I'm just looking to see whether anybody's got any questions. Just to reiterate the housekeeping that I said at the beginning, we have recorded this and we'll send you a link to the recording so that you can share it, or you can watch it again if you want. Question wise, let's see, we've got a question here. What do we expect from Java in the future? That is a very good question. I have a crystal ball. I shall look into it, and I shall say that I would expect to see some more things around pattern matching. I know that there's some ideas for extending that further within the language. I just saw in the last couple of days, I think it's JEP 500. So we've reached the 500th JEP, and that is about making final, which we talked about earlier, truly final. So you won't even be able to change it with reflection, deep reflection. I think that's a really good idea, because you never should have been able to change final. Final should mean final. So I think things like that is what we'll see. There will be plenty of other things that will come up in terms of all these different projects. So Valhalla is going to deliver at some point. We'll see more from Project Leiden. We'll see more from Project Amber, and so on. One other question here. If I want to move to Platform Core from Azul, do I need to change my application? No, you do not. So the Oracle JDK is built from the OpenJDK source code. OpenJDK is the open source version of Java. Oracle use that as the source base for their JDK. We also use the OpenJDK source to build our JVM, our JDK. So what you're getting is something which is functionally identical. We even run the TCK on it, so we can test it, verify that it matches the specification. That means you don't have to change any of your code. There's no difference. You don't have to recompile your code. You can simply take the same jar files, the same class files, write once, run anywhere. That also applies to different distributions of OpenJDK. Drop-in replacement, no requirement to make any changes or recompile. You don't even need to change any command line flags. All of those will work in exactly the same way. So that's the answer to that question. How is Java going to catch up with Python in the sphere of AI and machine language, or has it lost the battle? Yes, the perennial question about Java and AI. My feeling on this is, no, we definitely haven't lost the battle. I don't really consider it a battle. It's more a choice. And what we've seen is that if you look at more recent changes, and again, with a bigger project, what's called Project Panama. Project Panama was all about a replacement for JNI, which allows you to interact with non-Java library code. So code that's been written in C, C++, or whatever. And Project Panama introduced the foreign function and memory API, which gives you the ability to call and have callbacks from foreign functions and foreign libraries. And similarly, you can interact with memory in the same way. That allows you to interact with AI type libraries that are written in C or C++ and be able to use those directly from your Java applications. There's also some interesting libraries. So LangChain for J is one that's quite popular in that sense as well. So I definitely think that we haven't lost the battle. It's just a choice. And we will definitely see, I think, bigger applications will be running on Java once they need to scale up to bigger workloads. Okay, so I don't see any more questions, and I'm going to say thank you very much for listening, and this is the end of the webinar.